Welcome to the demonstration of AutoMag, Automated Depth Inversion of Magnetic Anomalies. There are a number of benefits in using AutoMag, such as realistic models for folded volcanics, ironstones and dikes. There's immediate validation in an interactive modeling context, that is, you can check the quality of your automated process. Automated strike correction for depth, susceptibility and thickness. There's a live filtering tool for rejection of unrealistic solutions. And there's easy quality control and manual editing of solutions during the final stage of the process. And once complete, you can export the solutions for use in other products. In this section, we'll talk about the tuning of AutoMag, where we'll apply auto strike correction using a trend azimuth grid. We'll focus on using a single cross-section, and we'll use the quick invert tool to seed the tuning parameters for a typical anomaly. For this demonstration, we're going to use a segment of a survey from the Al-Qidra region in the Northern Territory. The survey is flown with 400 metre line spacing and 80 metres terrain clearance. And on the left here we have the reduction to pole grid derived from the total magnetic intensity. That processing was done within the model vision environment. The area contains a set of folded volcanic units. In the middle we have either a syncline or an anticline. We can't tell at this stage what it is, and we're going to use AutoMag to show which of those two choices is correct. We'll use it to determine the depth of the fold limbs, and we will apply automated strike correction to the process. Now, for automated strike correction we actually need an azimuth grid. This grid up here on the top right hand corner shows the azimuth derived from the reduction to pole grid, where the reds here are showing an azimuth trend to the northwest, going over the top and changing to east-west to slightly northeasterly in direction. In the image below we have the confidence grid. That's the confidence of the trend calculation, and you will see that there is a high trend both along the positive limbs and the negative limbs of the grid. We don't need those for any visual processing at this stage, but the RTP confidence grid is a useful grid in its own right for picking linear features and disruption to linear features. The azimuth grid is used for the computation of the strike correction. We'll start with a single profile of data. We're much better off with AutoMag to focus on a set of characteristic anomalies to derive the tuning parameters, and we're going to focus on this part of the cross section. There's one anomaly here in the total magnetic intensity graph. Down below we have the path of the aircraft shown in blue, and below that we have the terrain surface shown in red. We'll start the process using the quick invert tool, which is a simple inversion for tabular bodies. It does a local regional correction if you have a grid in memory. We will use the total magnetic intensity since we're working off the TMI data. We'll apply a local regional correction, and I like to start with the first vertical derivative. When we click on that button, a graph of the first vertical derivative derived from the total magnetic intensity curve appears in this upper track. This is the anomaly that we wish to focus on, so we start by creating a seed. We drag out a section along across the anomaly, and we'll say we'll use that much of the anomaly as that appears to be unimpeded by adjacent anomalies. Let it go. It will create a starting model. It's not an inverted model, it's just a guess of where to put the model. Click on Invert 1 VD. It does a reasonable match. We can try once more to see if we can improve it. And then if we turn 1 VD off, we can actually invert on the TMI data. And we can see that we have a reasonable match. Switch back to the 1 VD and invert again. Now we have completed a single inversion which should give us a characteristic anomaly for the area, and we'll use that information to seed the AutoMag process. Here we will click on the AutoMag button to start the process. We're now ready to optimize the tuning. In the steps, we will modify the body width, depth and window size. That'll be an experiment to see how we can improve on the initial seed. And then we'll review the shape of the similarity coefficient curve to determine whether we believe we've achieved the optimal solutions. Quick Invert has introduced the parameters for the top depth to the body, the width of the body, and also the window size, and that window size matches the region that we dragged out across the anomaly. We turn strike correction on and we make sure that we've selected the trend grid for calculating the automatic strike correction. We click OK. We found 3 solutions. Note with the automatic strike correction applied that the body is slightly different to that of the model. Now we can start to tune the parameters by turning on the coefficients. The similarity coefficients are shown in the upper curve, and we can control the shape of those similarity coefficient minima by playing around with different experimental values. We can change the width or the depth to the top of 150. We could change the width to 100 meters, and we might round off the depth to 750 meters. Click OK. Minor change in shape. Little change in the depth of the solutions. But we might experiment on different type of data over a few different runs. Once we're happy with that, we'll start to run it across the whole map. But before we run it across the whole map, let's select the map and change it so we can more easily see the location of the solution. So we'll change the image at this stage to a grayscale image so that it's much easier to see the solutions on top. Click OK. And we can see the orientation of the solutions give you the trend of the inversion. Those look compatible with the anomaly trends that we've selected. In this step, we'll actually apply the tuning parameters to the whole map. That is, all the flight lines that are available. And first of all, we need to select the lines that we're going to run AutoMag on, and then we'll use the tuning parameters on all those lines. Selected. Now that we're ready to start on the map, we'll begin by bringing up the AutoMag control dialog. Select all the lines. They're automatically selected in this context, and we'll apply the initial tuning solutions to the whole run. Click OK. Said it found 66 solutions. And here they appear on the map view with some spurious solutions, which we'll filter out in a moment. Once we've completed the processing, we can then use the active live filter to remove inappropriate solutions. We'll show you how we trial different filter settings, and then once we're happy with those settings, we'll apply the filter to cull inappropriate solutions. Now we're going to activate the live filter so that we can remove spurious solutions. And a good example of that is negative susceptibilities, which are generated often from the negative or reverse side of the magnetic anomaly. So if we set that to 0, you will see a set of solutions have disappeared from this part of the curve. Now, geologically, I'm not expecting dips less than 20 degrees in this area. They'll be very shallowly dipping and difficult to interpret, so we can filter those. And I might want to set a threshold of confidence at, say, around 0.12. Remove any other spurious ones. We're only left with an occasional filter solution now that we're not particularly happy with. We could change the adjustment angle to 45. we might have removed just a couple more anomalies, and I can remove manually individual settings that I feel are inconsistent with the geology. Now that we've applied these filters, they have not actually been applied to the model. We can save those settings, click on Save, I can close, we haven't lost any. But if I run the filter again, use the current default settings and apply the filter, they will be removed for good. The solutions, and we'll annotate the depths. We'll build a 3D model from the solutions. We'll then visualize that 3D model, and then we'll show you how to export the solutions. We'll start by turning on the annotations for the AutoMag solutions. Choose the AutoMag solution option, click on Configure, go to Channel Annotation, turn on the annotation and select the various parameters such as font size, offsets and angle. Click OK. Here we have the depths annotated along all the solutions that we believe are appropriate in a geological context. The next step we'd like to do is to determine whether this fold axis is a syncline or anticline. So we'll do that by converting it to a 3D model in Model Vision. So we'll select all the solutions, we'll convert those points to bodies, we will terminate the bodies at sea level so they don't have infinite depth extent, and we'll set the strike length to 500 meters, which will allow them to reach from one line to the next. Click on OK. The bodies have now been created, although invisible in the map view, but the next stage we want to do is visualize them in 3D. Go to the View menu, click on Perspective View, choose the 3D Navigate option, and here we can see the solutions, and clearly we have imaged a syncline. So very quickly we've got a geological answer. We've not only got the depth information, we've determined that this is a syncline rather than anticline. The next step we want to do is export the solutions, so we'll close that window down. We'll go to the File menu, choose the Export option, click on Point Data, and we'll export to a CSV file so we can have a look at it. Save it. Choose all the lines. For simplicity, we'll choose all the coefficients. Click on OK. This is the file we just created. Double click on it. And here we can see the solutions. And this can be imported into a PA or a range of other products. The values can then be culled or selected and used in whatever way the interpreter sees fit.